College Board gave us a built-in cheat code of a graphing calculator on the digital SAT, and most students just aren't using it anymore. I was the last person in the room on the day of the SAT and still walked out with a 760 in the math section. Today, in part 2 of our series, I'll be showing you the exact desmos hacks that not only save me tons of time on test day, they also help me solve impossible algebra problems in 5 seconds without writing down anything. With all the wonderful functions and features of desmos to choose from, I'll be touching on 3 specific points that crop up the most, with a practice problem for each. Let's jump straight into an example of systems of equations. Alright, so the problem that we have here is asking about a given system of equations with a constant of p, so we don't know what p is. If this system has no solution, what is the value of p? So this question can be pretty intimidating to look at because we have not 1, not 2, but 3 variables in this equation. The thing is, most students would probably try to tackle this question by plugging in random values or maybe trying to isolate variables, but there's a better way to do it. Once you realize the true power of desmos, this gets a lot more straightforward. So the best course of action, of course, is to just plot these systems of equations. When you get to this point, make sure that you add a slider for the variable that you're trying to solve to. All right. So if you read the question again, and we're seeing that we're looking for a system of equations that has no solution, what we're essentially looking for is a system of equation where both lines are parallel and never touch. So we're now trying to find whatever value of p that we can place into this equation that will make sure that these lines are parallel. So you see, all we have to do now is use our slider until we get to a value that looks about parallel. Once we get to, say, 5.3, I'd probably say 5.7 actually looks pretty parallel. What we now need to do is zoom out. It's important to zoom out because we need to see if these lines end up touching at a point later in time. And if we get here, we can see now that the lines do intersect with a p-value of 5.7. So let's readjust our line. So now that we've tested 6, let's zoom way out, get to a much further point down on the graph, just to test things out. And once we've zoomed in enough, we can actually see that we've still preserved the exact same line that we had beforehand. So moving back to our home, if we do see the similarity between those 2 points, then we can pretty much simply deduce that in order to make these lines parallel, we had to have a p-value of 6. Let's move on to the next question. So now we're looking at a question asking which quadratic equation has no real solution. What some students might try to do here is plug all 4 of these equations into the quadratic formula and see which one gives them an imaginary number. There is a much faster way to do that. If you open Desmos, all that matters now is you going in to plot the equations. All right, now that we've got all of our equations plotted and we're making sure that they're all different colors in this window, we can now zoom out to see which one of these graphs has no real solution. Remembering that for a graph to have a real solution, its graph has to cross or at least touch the x-axis. As we can see with our answer choice B right here, how it does touch the x-axis while not necessarily crossing it, so it does have one real solution. If we zoom out a little bit more, we can actually see that our blue graph here, which is the answer choice D, does not touch the x-axis. That's all we have to do. Since D never touched the x-axis, that's going to be our answer for this question. Finally, let's move on to a problem that involves regressions. So we're looking here at a scatter plot showing a relationship between 2 variables, x and y, for a given data set. We're also given a line of best fit on this graph. So we now know that data set F was created by multiplying the y coordinate of each data point from data set E by 3.9. So what we're now trying to do is see how can we create an equation of a line of best fit for data set F. A lot of information there. But the key things to note are that dataset E is the exact same concept as dataset F, except we're going to make sure that every single point on our line is multiplied by a factor of 3.9, as shown in the question here. What do you do here? There's a number of ways that most students would try to go about this. They would maybe try to guess what the line of best fit looks like from looking at the graph. Some might try to plot each point on a table, or even start trying to do some algebra. But there is a way to do this, and it involves regression. So let's go ahead and set up our regression here in Desmos. First things first, we need to find out what data set E is. So let's find the line of best fit for that line by simply looking at the graph. We can see that if we look at our y-intercept and a given point on the line, that our y-intercept is at 0, 12, and we have a point on the line at 12, 30. Given this, what we can now do is create a table, and let's input these values in the table. Perfect. Now what we can do here is add a regression. So now we see that we've added a regression, and with this regression, we've been given a line of best fit for this data set. All right, now that we've gotten that part done, here's where the hard part comes in involving a regression. So what we're trying to do here is take this data set and multiply it by a factor to get another data set that we're looking for. And regressions can do a whole wide world of things. There's numbers of videos online that can truly display the power of regression. But what I'm going to do here is show you the specific case of how you could use regression. So let's make sure to use a correct notation here of our y1 with a tilde sign instead of an equal sign. And then of course, let's put in our slope-intercept form of mx1 plus b. Now, if we do review what we have here, we can actually see that we got the same exact equation since we put it in slope-intercept form. What's important to note here is that the question asks that data set f would be multiplied by a factor of 3.9 from data set E. So what we now need to do here is, since this is our y-coordinate, we're taking our y-coordinate and multiplying that by 3.9. We now see that we don't have a line anymore. However, what we do have are parameters for our regression. If we look at the slope-intercept form given to us, we can see that 5.85 is equivalent to x, and 46.8 is what's equivalent to b now. Meaning that if we now take this back to our answer choices, we can see that the answer choice that most closely relates to this is going to be answer choice A, because we have our b value of 46.8 and our m value rounds up to 5.9. Alright, so here's a quick warning. Desmos is a great tool, but it's not a replacement for your brain. The four biggest traps that students usually fall into with Desmos are zooming and scaling errors. If your lines look parallel, zoom out. Like the question that we had earlier, that line might intersect at 100, 250. Syntax error. Forgetting to use the correct formatting during regressions, tables, or expressions will typically give you an error. Clutter. When moving from problem to problem, students might forget to remove all the worker equations they had from a previous problem. They may also forget to at least differentiate calculations from previous unfinished problems. And most importantly, overcomplicating things with Desmos. There are times where students may know how to use a problem, but may try to use Desmos instead because it seems as the easy way out. Once you can get consistent enough with Desmos, it'll easily pull your score up into the 700s. If you want to reach that elite range though, you've got to eliminate silly mistakes. In part 3, I'll be breaking down the careless errors that cost me points on my practice tests and how you can stop them. I'll see you in part 3.